Hello, everyone. This is the solution for the homework for the three torque problems on the back page of our worksheet. So I know we went over them in class, each group did, but I just wanted to put this out there for those that need more detail. So here we have our first problem, the one with the table. So we need to figure out where we can sit, what distance from the edge of the table. So I'm going to envision sitting on the right-hand side. So how far from this point or on the left of this point can we sit without tipping over? So the first thing we need to do is identify our axis of rotation. So if we sit on the right side, the left leg of the table is going to go up and we're going to pivot around that right leg. So you can envision this as our axis of rotation. So your distances or your radius for each force or torque can be measured to that point. So let's identify where the torques are with drawing our forces on here. So one, we're going to be putting, a person, say right here, and the weight of that person is going to apply a force. So force due to gravity of the person is going to apply a torque, causing this table to rotate to the right. Then we have the weight of the table itself. So the weight of the table, we're assuming it's uniformly made, is going to act in the center of the table. So right at this 1.1 meters in the middle from either side. So the weight of the table. And that's it. There's no other forces involved, no other objects causing our torque. So we're going to have our net torque equation equaling 0, or I like to just say, since there's only two here, they would equal each other, just opposite directions. So we're going to have the torque of the table, the weight of the table, equaling the torque of the person. And torque is FR sine theta. We're not concerned with sine theta here because sine 90 is 1, so we can kind of leave that out. And I'm going to identify what specific forces, or I already identified the forces, but I do want to include them in my calculation. So we're going to have essentially torque is equal to FR, in this case FG, and I put T for table, and RT for table, meaning the center of gravity of that table. And then we have the weight of the person, and we're solving for where we need to go. Where can this person sit? So the radius of the person. We don't know the weights, but we do know the masses, so we can derive this equation further. Fg equals mg, so the mass of the table times g, radius of the table, mass of the person, g. Oh, we see that it's a gravity party, so we take gravity from everybody, and radius of the person. So we get rid of gravity, and we have the mass of the table is 24 kilograms. And that's going to act, since we're looking as this is my axis of rotation, we only need this distance here, how far we are from that right table leg. So since we're given the distance between each table leg, the 1.2 meters here, half of that is where we're at. So change colors, 0.6 meters. And the mass of the person, 66 kilograms. And we're going to solve for where they're at. So we plug that into a calculator. And we get about 2.2. Nope, sorry. Around that to 0.2 meters. It's 0.218, but we'll just round to 0.21 or 0.2. But that's not the answer to the question. That's where they're going to sit relative to our our axis point that we defined. We want to know how far from the edge of the table. So if this portion is 0.2, if this portion is 0.2, and this isn't the scale, this other section would have to be 0.3 because we know that full distance from the edge of the table and that right table leg is 0.5. So the full answer would be that we are going to sit 0.3 meters from the edge of the table that's right here. Okay, moving on to our next problem with the 3 children, A, B, and C. We look at this scenario and we need to figure out where to put child C. We see that we have 2 children already on the edges, and since this child A is more massive, then we would have an overall torque going to the left or counterclockwise. So we would need to put child C on the right-hand side to equal out that torque, but we don't know where to put that child. So we're going to put them here. So we're going to have a force caused by child A, which then in turn is going to cause a torque. We're going to put child C here. And then child B. So I identified the forces. And if this is my axis of rotation, that rock, my net torque equation would look like this. So the torque from A would equal the sum of torque, we'll put C plus B. And torque is force times radius, so it's specifically the force of gravity of each kid multiplied by how far they are from that axis of rotation, the rock, which we can call radius, R. And we could define that further because we're not given the forces. But we do know force due to gravity equals mg. So the mass of A times g times the radius of A, and that continues for the other children. And we see yet again, we have a mass party. So non-mass party because they're different masses, A, B, and C. It's a gravity party, so we take gravity from everybody. And mass of student A is 45 kilograms, sitting, so it's a 3.2 meter long board. So half of that, each kid, A and B, from the beginning is going to be 1.6 from that. The mass of child C is 25 kilograms, and that's our unknown. We don't know where to put them. So we plug all that into our calculator. Let me just double check that I have the correct answer. And we get a radius of 0.64 meters, meaning from our axis of rotation that we defined, that distance here would be 0.64. And finally, our last problem. So this is the first problem we've seen where we have forces at angles. So we have to incorporate that full torque equation, being torque equals Fr sine theta. The sine theta belongs to the force, so that we're looking at that perpendicular component of the force. So for our traffic light, This is our lever arm. This is the object that's rotating about contact point A at the bottom, because there's a bolt there. So let's look at our forces. Well, we have the weight of the traffic light, called FGL. We have this cord. What do they call it? Cord. Tension in a cable going this way, preventing that torque caused by the weight of the light. And sorry for my blue class, we did unfortunately miss a force, and that is the weight of the pole. So the pole has weight. So even if the light didn't hang from there, the pole would potentially rotate. So since this is a uniform aluminum pole, they tell us there, oops, the weight of that pole, or the center of gravity of that pole, is going to act right in the middle of the pole. So right here, we're going to have another force that's caused by the weight of the pole. So we have three forces causing the rotation about that axis A, and we're going to have three torques. So we're going to have our net torque equation equaling 0, or the clockwise torques equaling our counterclockwise torques. So it's going to be torque from the tension in the pole, tension in the cable, torque from the weight of the pole, plus the torque from the light. So same thing as we've been doing, we need to define those forces. So force tension. The radius, well, this is going to be the radius from A to D. And sine, we have that angle 37 degrees. I'm going to run out of room. So just bring this down here. And the torque from the pole to the weight of the pole times the radius, which that's going to be, I'm just going to put center of gravity for now, and sine some angle. So we're going to be looking for these angles here. Then the weight of the light is our other force, times radius AB, because it's the full length of the pole, it's at the edge, and sine theta. So that's our full equation. This is 90% of the work. The rest of it is geometry and some basic math here. So let's see what we know. We're solving for the force tension, radius A to D. So we're looking for this distance here. So we do have a triangle. We have an angle in that triangle, and we have a side of that triangle. So that means we could find either side. So we could incorporate this right into the problem, but I'm going to do it as a little aside. So I have the opposite side of my angle here, so I'm going to use sine 37 equals opposite, so my 3.8 meters, over my hypotenuse, or really A to D. So if I plug that all into a calculator, I get AD equaling 6.3 meters. So I have that radius. I know sine 37. FG equals mg. So I'm going to take the time to write that out. I probably should have done that first, but it's always a good idea to show each step. So this is a case where gravity doesn't exist everywhere, meaning it's not in all parts of our equation because we can't take it from the left side because it's a tension force. So we have the mass of our pole, which is 12 kilograms. G, I'm going to use 9.8 today. Radius CG, so center of gravity of our pole. So if the pole is 7.2 meters long, half of that is 3.6. And sine theta. So let's look at where to find these angles. So what we're actually looking for is the components of gravity that are causing our pole to rotate in that direction. So where do we find these angles? Well, we'll visit back to geometry class. For this triangle, it's a right triangle, and we have, obviously, the 90 is at the top, we have the 37, and the missing angle is 53 degrees. So we can also see, depending upon how you look at it, that these are alternate interior angles. Maybe another way to look at it, if we don't see it directly, is having two similar triangles, or complementary, I forget what the proper term is. But we do have these as being alternate interior, so they're equal to each other. So these angles are both 53 degrees. And we're almost done. So with the mass of the light, 21.5. And I'm going to run out of room. Radius AB is at full pole. So we just plug everything in to our calculator, and depending upon rounding, we get a force of about 408 newtons for the tension in our cable. So that's all part A. Part B looks for us to determine the forces on the bolt here. So let's erase some of this. So we're looking at the forces on this bolt, the vertical and horizontal components. So we already know that the tension right here is about 408 newtons, or 409, I think it was, rounded. So again, everything we do, we're condensing this pole to a dot, a particle. So if we're pulling this particle to the left, this bolt has to prevent it from moving to the left by applying a force to the right. So the force from the bolt in the x direction is going to be the same as the tension in the cable. That bolt also has to support both the weight of the pole and the light. So the vertical component would be the sum of those two masses. So we have 12 kilograms plus the 21.5 kilograms times 9.8. And we get about 328 newtons. So the vertical component on the bolt is the 328, and the horizontal component is the 409.